We present Strumming to the Beat, audio conditioned contrastive video textures. Given an input video, we synthesize a new video that matches the conditioning audio. We first consider unconditional video texture synthesis using visual features only and no audio. Our approach is inspired by video textures, a classic non-parametric video synthesis method which converts a single input video into an infinitely long and continuously varying video sequence by stitching together parts of the input. Given this 3-second clip of a candle flame, this method synthesizes a 10-second clip by finding alternative, plausible transitions in the input video to produce different yet dynamically consistent videos. The red bar at the bottom indicates the part of the input video that's being played. However, classic video textures uses Euclidean pixel distance as a similarity metric between frames, which makes it brittle to videos with irregularities and chaotic movements, like dances or musical instruments. For example, given this video of a person playing a guitar, the classic method produces jarring transitions. A natural approach would be to use GANs to solve this problem. However, state-of-the-art GAN-based video generation methods such as MocoGAN produce low-resolution outputs and struggle to match the realism of actual videos. For example, here we train MocoGAN on the 3-second video clips of the candle flame and the guitar shown earlier. The synthesized output videos contain artifacts and do not reflect the temporal dynamics of the input videos. In this work, we investigate contrastive learning approaches for graph-based sequence generation. We propose contrastive video textures, a non-parametric, learning-based approach for video texture synthesis. Our method uses learned feature representations and a distance metric to compare frames and produces a smooth video with seamless transitions. The red bar at the bottom indicates the part of the input video that's being played. Here is an overview of our method. Given an input video, we extract overlapping segments from it. Next, we learn feature representations and a distance metric for these video segments by fitting a bigram model. Given a query segment, the model learns a representation that is similar to that of the positive segment and dissimilar to the learned representations of the negative segments randomly sampled from the rest of the video. The model is self-supervised and is trained using contrastive loss. During inference, we start with a random segment and use the fitted bigram model to compute the edge weights to the remaining segments in the video. To introduce variance in the synthesized textures, we scale the temperature to modulate the sharpness of the softmax distribution. We denote higher weighted edges in green and lower weighted edges in red, and the thickness correlates with the probability. We randomly traverse along one of the higher weighted edges to reach the next segment. Both segments are then appended to the output and the process is repeated, with the second segment as the query. Given an input video with audio, we extract video and audio segments. Next, we use the fitted bigram model to compute the edge weights and the transition probabilities for the video segments. Now, given a conditioning audio, we divide the audio into segments of the same size. We then compute similarity between the features of the first conditioning audio segment and the input target audio segments. This is repeated for the remaining audio segments in the conditioning audio to construct the audio transition probability matrix. Finally, the two are combined using a weighted average to form the final transition probability matrix. The audio conditioned video texture is then synthesized using the same inference procedure described earlier, just using the updated transition probabilities. For the unconditional setting, we compare our method to the classic algorithm and its variants. The classic method completely fails to find good transitions and loops over the first few frames, appearing to be stuck. The red bar at the bottom of each video indicates the part of the input video being played. Classic Plus, like Contrastive, appends multiple frames to the output sequence instead of a single frame. Classic Plus Plus adds a stride while filtering the transition matrix. Both Classic Plus and Classic Plus Plus textures are slightly better than Classic, but lack diversity and produce jarring transitions. Classic Deep uses ImageNet pre-trained ResNet features instead of raw pixel values. The output texture is choppy due to multiple poor transitions chosen by the model. And finally, here is the result from our method. The contrastive method is the most realistic and consistent with seamless transitions. The red bar transitioning to new positions indicates that our textures are dynamic and diverse. Visual rhythm and beat warps the input video to match the beats of the conditioning audio, but as seen, the video and audio are not synchronized. Random replay overlays the conditioning audio on a random section of the input video. We observe that the audio and video are misaligned. Audio nearest neighbor computes the similarity between the conditioning audio and the input audio, and then extracts the closest match. Again, the audio and video are misaligned. We add audio conditioning to the classic video textures algorithm. As seen, it fails to produce a smooth output. Here are the results from our method. The videos synthesized by the contrastive model align best with the conditioning audio. It identifies gaps in the audio, detects change of pace, and produces a semantically meaningful output. and a conditioning audio. Thank you.